Good morning, everyone. I hope I can be very well heard. Also, thank you very much for joining the class. So last time we discussed about convolutional neural networks, and we discussed about how the convolution operation happens, and then how the layers are stacked up. And we looked at LeNet 5, and we looked at AlexNet also. So today what we want to do is we can relook at LeNet 5, which is the very old CNN that was built by Professor Jan LeCun. And we will try to implement that in PyTorch. And then we will look at how neural networks, convolutional neural networks can be trained. Little things that we need to know, but those are very important things when we want to get them trained. So that's the plan for today. So as usual, please do not hesitate to ask questions. You can use the chat to ask questions, so you can always turn on the mic and ask questions. You're most welcome to do that. Also, there is the quiz that is on convolutional neural networks. Please answer that question also. It's a simple quiz. Yes. Okay. So let's briefly remind you some things now. We realize that we can convert an image to be represented by a vector. So here it's by 1, 2, 3, 4 numbers. Actually, we know that an image is larger than that. But if we represent with 4 numbers, we have these weights rows in the weights matrix W, and then we multiply them with this, and then add the bias, and we get a cat score, dog score, sheep score, and so on. So based on that score, we can classify whether it's a cat, dog, or a sheep. Right now, as the dog score is very high, we call it a dog score. Now, the problem is these weights are not properly tuned or not optimized. That's why the dog score is high in this case. The cat score should have been higher, right? That we studied. And we studied the perceptron, and we studied about activation functions briefly. Today in the afternoon, in the latter part, we will study that further, and we look at gradient descent in slightly more detail. And we looked at convolution, how convolution happens, and we were able to look at the batches, convolution kernels, and how multiple kernels give rise to uh, these feature maps. And then when you have a batch of 4 images, how 4 of those stacks of feature maps generate in the output. Yeah, we looked at all these things. And then we looked at how the input image comes, and convolution, nonlinearity, and spatial pooling are usually stacked up. And today we will look at batch normalization also. And then we looked at this important ReLU nonlinearity. We will look at that further. And then max pooling operations and the structure that was there in the AlexNet, conpool, 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 and the 3 dense layers. Um, then we look at the padding aspects, the receptive field. Then we looked at different convolutions, and we did a small example also. And then this convolution summary is very important based on the input number of channels. RGB image, it has 3, scene is 3, and the size of the image. We can find the size of the resulting image if you know the size of the convolutional kernel, the padding, and the stride. Yes, so these were the things that we studied last time. And then we studied the LeNet 5 in detail. So now we will relook at it, and then we will implement that in PyTorch. Okay. Yes. So to briefly describe LeNet 5 once again, mm, you can see in this one, the images are inputs of size 32 by 32. Actually, we can even write 1 times 32 by 32 to signify these are grayscale images as opposed to color images. Then there is this convolution operation, which gives rise to 6 feature maps in the output. What that means is that this one is using 6 convolution kernels. And also, as the size reduced from 32 by 32 to 28 by 28, we realize that this convolution kernel is of size 5 by 2, 5, 5 by 5. What's the reason for that? I hope you remember when you have an image and you overlap a 5 by 5 kernel on the image at the top left corner, let's say. So you can see the most extreme position of the center of that kernel is at pixel 2, 2, right? Can you see that? 2, 2, 0, 1, 2. Pixel 0, 1, 2, 0, 1, 2. So as a result, you see you lose a certain number of rows. So here we lose two columns, and we lose two rows in the output. Yeah, that's why you got the size reduced to 28 by 28. So therefore, we know that it's a 5 by 5 convolutional kernel that has run. Yeah. So then they have the subsampling. This is we call it max pooling, but in this one they used average pooling. So we will implement the original network with average pooling, not max pooling. Sigmoid or hyperbolic tangent nonlinearity. These are not good, but we will implement that and say, and then here you can see it is stride 2 max pooling. That's why the size has become half. 28 has become 14. And then again, another convolutional layer. So there you can see the size has become 10 by 10. So that means the size has reduced by 4 from either side. So once again, we know that these convolution kernels must be 5 by 5. And how many kernels? 16 of them. That's why the output structure has 16 channels. And then once again, the subsampling layer or the max pooling, you can see the size has become 5 by 5. That means it has been divided, each site has been divided by 2. Therefore, we know that it is doing a stride to uh, average pooling. Then this structure we realized is 16 times 5 by 5, the 400. 400 numbers are there. Those 400 numbers have been connected to 120 numbers. That 120 has been connected to 184 numbers. Those 84 have been connected to 10 numbers to complete the network with the dense layers. So this is the network. So you have to keep this network in mind. Maybe if you like, you can have a screenshot, you can have this image beside you, and you can start your Google Colab or you can start your VS Code so that we can do the coding. So I will start the coding now. So we can learn a lot if you know all these things. Yeah, I apologize. Some of you already know these things, I know, but if there is someone who does not know, we have to do it now. So we will do that. So of course now you know that I do it here in my VS Code in class 2025 9:30. All right. So since everyone is using PyTorch, we will also use PyTorch. Increase the size a little. So, all right. I hope everyone is ready. Yeah. Import PyTorch. Import Torch. Import Torch. Oh, I did not save it as a. Sorry about the interruption. So if you use this one of these markdown ones, you can even write what we are coding now. Actually, what we are coding is Lenet 5 with, of course, with MNIST data set, right? Data set, and we what we want to do is the original implementation, mimicking the that means we will use hyperbolic tangent activation, average pooling, optimizer. We will study about these things, optimize and so on. Let me see whether we can use stochastic gradient descent. Let me see. I'm not too sure whether that will work. But we'll see. Then you go for a code block. Then you can say import torch. That's fine. I don't know why these colors. I'm not getting the colors. Okay, let's see. Import torch neural networks as NN. We see why I'm not getting the colors, so it is annoying. Shall we open an old file that we did? Was that right? Wi-Fi MB. That's right. Oh, this is a plain text one I'm using. Code. Something is wrong. I need the colors. I'm sorry about this. Yeah. I think I created it as a plain text file. That's what happened. Import torch. That's fine. Okay, now you can see it's prompting me, so it's okay, but this is not something that you should do. So I'm inclined to hit tab and get it done. So it's giving me everything. So everything I will not do, but this importing things I will do. Mm. So import. Now we need the optimizers. Torch, optim as optimizers we need. Then we need data sets and transforms. That's okay. No big deal. We get that also. And we need data loader, and we need the random split also. It knows everything that I'm trying to do. And to matplotlib as pyplot to plot something. This we do not need. So, okay, let's look at define the Lenet 5 model. Okay, so now we need to have these keywords, class Lenet 5 inherited from neural network module. Then I will turn this thing off. Wait, correct off. Right, or knowing. Okay, I want to type this properly. These things are there. If you know Python, I ask you to study. I think this will be well known to you, but otherwise, that's okay. So, okay. Self, that means I'm referring to this class. Con1, first convolution layer equals from the neural networks I am writing. Now, con, these are the important things, 2D convolutions. One channel as the input, six output channels, kernel size is 5 by 5. Hope I have not made a mistake. Okay, now after the first convolution layer, this is the first convolution layer, which is 5 by 5, is it? And then we have a subsampling. They call it subsampling, but we know that now we call them a pooling. Self pool one, that's a name that you are giving, equals in dot average average pool in 2D, average pool in 2D, because we are handling images, and 2 by 2. And the stride is automatic for 2 by 2 pooling. Stride will be 2. And then next we have, after that pooling, we want to do exactly this one. Another convolution layer, 16 maps. Input depth is 6, as you can see. Depth is 6. 1, 2, 3, 4, 5, 6 layers are there. And 5 by 5 convolutions. Yeah. So now self dot on 2 in dot. Can you do the completion? So can you do it, send me some messages so that I know, please complete this. Please complete this as you see on screen. So let me see. Some of you are already giving me answer. That's the answer is correct. Thank you. Two people have answered. Yes. There's another person who has correctly answered and he has given the next layer also. That's very good. Others also, please try to answer. Okay. Okay. I will write this on 2D. Input number of channels is 6. output number of channels is, was it 14? 16. 16. 16 and the kernel size is 5. So you can see it is prompting me at the top. This is nice. That kind of help is nice, but full chat GPT help is not good. All right, then self dot pool 2 equals nn dot average avg pool 2d. That's once again 2 by 2 pooling. Okay, then we have another convolution layer, I think. Then another convolution layer. That this is after pooling, you have this map. Mm, then we have to flatten that, right? Yeah, flatten that. So then after that, we have the uh, linear layer from we layer from 400 to 120. FC1 equals n dot linear. I mean, these layers are called linear layers. Linear 400 to 120. Then after that, one more linear layer, FC2, nn dot linear, 120 to 84. You can see this, there are 400 numbers here. That's why I write 400 to 120, 100 to 84, 84 to 10. FC3 equals nn dot linear, 84, 84 to 10. That's it. That's the network model. And then we have to define the forward pass. The forward, that's all we need. Backward pass, that means the gradient descent, then this will do. PyTorch will do. So, okay. Now, um, it receives an X, that's an image that we have to properly give. Then the output X is torch dot and H self conv one X. I hope it's clear for you. We take the image and apply to our con1 layer and put the hyperbolic tangent activation there to get the output map. X. Now what we have to do? Self dot pool 1 X. Take the output X, put it to the pooling one. Pool one, this one. Then again something like this, right? Okay. It's very easy now. We know exactly what to write. Put and itself con2 and hyperbolic tangent, then pool 2, second pooling layer. Now we have that structure. Then we have to flatten that. X equals x dot weave, x dot size 0 minus 1. So I hope these are correct. Flattening. Then x equals torch dot tan h. Tan h. We have to get the self dot fc1 to be given this input text. And then similar layers, fc2 and fc3. That's all. I hope these are okay. So we can just save it and see what happens. You see, is there a mistake? There's no mistake. Now we have to get the data and uh, annoying things have to be done. So those things I will copy and paste from the file that I have. First of all, we have to uh, change. Now this MNIST dataset that we get is 28 by 28 images. We need to convert them to 30 by 2 by 32 because in the original architecture, he has written 32 by 32. So with respect to that, we will have to do that conversion. So now I'm going to do data setup. Data setup. Knowing the things, okay? Transform. We define a transform uh, equals transform dot compose. Is it correct? TRANS forms, transforms. Transforms dot compose. We had to do the padding thing. So these are annoying syntaxes. So pad 2. Now 32 will become 20 by 20 will become 32 by 32. So then we will have transforms to tensor, convert into tensor. Let me write a comment there. 28 times 28 will be padded to 32 times 32, right? Here. Transforms that pad to transforms to tensor. Okay, that part is done. Then we have to get the training set and the testing set of data. Full train or something equals data sets. Now this we have imported at the top where you can see Torch Vision data sets have been imported. Data sets and dot mnist. Yeah. Then we have to say where we are going to put this data. In this file data folder, train to. I have this file with me, okay? I'm not typing on my own. I don't want to make a mistake. Download equals true. Transform. Transform. So when we do apply this transform, it will pad and convert to a tensor. And this one, I want to do test also. Test. This is the test data set. Dataset mnist. Root is the same thing. Train is false. And then download the true transform, transform. That's fine. Then splitting, we have to split the data set. 50,000 for training and 10,000 for testing. Train data set. Train data set. Validation data set. We can use I don't think this line is even required. Let's do it. Train dataset, val dataset equals random split random split from the full trade. We want to get 50,000 for training and 10,000 for testing. And generator torch dot generator and seed, whatever that's you put a seed, otherwise this is the to control the randomness of this extracting data from the files, data from the data set, the data loader. So then we have the train loader. So these help us to get images in the size of the batches that we want. Train data set. From the train data set, we get batch size 64, let's say. Shuffle. So for the test loader, so these are annoying things that you have to do. Test loader, data train data set, that this is from now we get from the validation data set. Now we will get batch size in 1000. It doesn't matter. Shuffle is false. Um, then we set up the training process. If you have a GPU, this line is important. Torch dot device. I think my GPU will be used. I have a small GPU in my machine. Device CUDA. If torch dot CUDA dot is available, else CPU. I think it's very clear, right? If GPU is there, it's GPU. Otherwise, CPU. These are okay. Model equals the linet file that we initialized at the top to device. Okay, that's fine. And criterion, that is, what is the criterion for evaluating the loss? Neural networks cross entropy loss. We will look at this loss, hopefully. Optimizer. Optimizer. Let's pick Adam first, and if it doesn't work, if it works, let's go for stochastic gradient descent. Adam is the safest one, as you know, and it's very fast also. Learning rate 1 e minus 3 or something. Okay, let's run this and see if there's a mistake. It's a mistake. Doesn't apply to int object. Torch generator. It is a mistake. Random split. Full train, that's okay. 50,000, 10,000. Generator. Oh, the generator forgot that. That's the problem now. Okay. What is the row number? Yeah, let me resolve that later. I will write it and I will look at it later. I don't know how to resolve it now. Maybe I made a little mistake. Okay, now optimizer is fine. Mm. Now we have to record the mm, parameters, logging. To record the parameters, we'll have the batch losses. So we feed one batch at a time of 64 for training, and we want to record the loss so that we can plot a graph. Train losses for each epoch, that means the whole 50,000 data set, we will record that also. Validation losses for each epoch, the validation loss. Epoch means we run the full data set through the network. And train accuracy, train accuracies, and test validation accuracies. Okay, those arrays we hold, and then we write epoch, number of epochs. Let's do about 5, mm, 4. Now for each epoch, you will see what we will do. For epoch in range from 1 to epochs, 1 to 5, 1 to 5, 1 to 5. Now we do the training. Um, model dot train. Running loss, comma, correct total equals 0.0, 0, and 0. Okay? Just to keep these statistics also with us. For data, comma, target, image, and the correct number in train loader. Now you can see how easy it is when you have this train loader and test loader. We don't have to worry about it. It will give you the number of batches that we have data, comma, target equals data to device and target to device, CPU or GPU, optimizer. So we have to zero the gradients, zero grad, um, and output equals model dot model data. So we feed the data to the model and we'll get the output. And once you have the output, we have to compute the loss by applying the criterion, output, and the target, right? So these things are easy. Then we get the loss. And you can see the most important operation here. Right? So this will calculate the gradients, and we say optimizer dot step. That's all. Okay, then we have to do some bookkeeping activities to record these losses and so on, so that we can plot the graphs. Batch losses dot append loss dot item. So some of these things I know you have to memorize. Item. And then running loss. It's prompting again. Running loss. loss dot item data running loss. Yes. And predictions. Predictions. Output. Argmax. That means we get which class it is, argmax. And then, okay, you can understand this language, right? If the prediction is equal to the target, we increase the correct ones and the total target dot size. What is it saying there? It is going to put everything here. Yes. We hope that these are okay. Then outside the second loop, we want to go to the first loop, train losses dot append running loss divided by the total, train accuracy is append percentage. Oh my goodness, everything it is giving. So actually these are not so important. So maybe I will get these prompts done. Evaluating. Okay. Congrats. Yeah, all these things are there. So I don't think that these are so important for us. These are all correct. And then the plotting part also I'll let it handle. So this, all these things are correct, but this earlier I have to handle now. I don't know what happened to that. This one. Can someone help me to understand what has happened? What did I do?
Double underscore after init.
Thank you very much. It is saying this error loss criterion output target. That's a mistake here. Hmm. Have it all coded. Let me check that error. Hmm. Spelling mistake. Entropy loss. Correct. Okay, I will have the code that I have written at home. So it's slightly different, but this I do not want to check now. I have it here. So there you go. I have run that. Maybe during the break, I'll try to correct it. So you can see when you run that, the accuracy. Uh, Now these are epochs means all 50,000 is sent to the network. Then accuracy has become 90.66% training accuracy. and validation accuracy is 95%. So you can see the training accuracy is improving, validation accuracy is improving, and validation loss is there. It should become greater than the training loss usually. Uh, you can see the so-called loss curve. That means you can see the batch iterations. You can see um, for each of the batches, each of the 64 images, we compute this loss and we plot it. So that's why it's noisy here, because the data distribution is different. So therefore, it is having different losses when each batch comes. So you can see that the Linet network. So in this one, this is slightly different. I think this has one more convolution layer. So what we implemented, this structure is very similar to the what we have in the slides. And these are the two things that you need to understand. Other things are supplementary, so I may have made a mistake somewhere. So during the break, I'll try to correct that. Okay, let's get back to the slides. So you should know how to implement a neural network drone like that um, in PyTorch. So it is not very hard. Then last time we studied about AlexNet, and then we studied about the nature of those memory usage, then the parameter count and the number of floating point operations and so on. We studied, if you remember. And then we stopped here. So after the AlexNet, Xyla and FergusNet came as the 2013 winner. It is similar to AlexNet, but they made some changes. I will not go into details about this. Then came the VGGNet. This was an important contribution because in the AlexNet, the design was not principled. So they came up with some principled design. They said, okay, all convolutions must be 3 by 3 convolutions, stride 1 and padding 1. Max pooling are 2 by 2 max pooling stride 2. After the pooling, double the number of channels. So you can see this is the AlexNet. So input image, 11 by 11 convolution pool, 5 by 5 convolution pool, 3 by 3 convolutions, and then pool, fully connected, fully connected, fully connected, and a softmax layer. Then if you think about this VGGNet, we have the input image, 3 by 3 convolutions, and then a pooling layer, then 3 by 3 convolutions, then a pooling layer. You can see, as they said, after the pooling layer, number of channels will be doubled, 64 to 128. So here, 128 to 256. And so on. So you can see that's the VGG16 that they constructed. So there is some principle for people to, when they design networks, the final part is the same. So it has much more parameters, consumes much more memory and flops. So if you compare with AlexNet with 5 convolution layers, VGGNet has 5 convolution stages, as you can see. You can see 5 stages over there, 5 stages over here. And stage 1, con pool, stage 2, con pool, these con pool, and there's one more convolution if you go to VGG19, as you can see from here. So I hope VGGNet is also clear. So if you like, you can look at this diagram and you should be able to implement this in PyTorch. Of course, implementing the first one is the cumbersome one. After that, these things are not so hard. Okay. So one more thing is the advantage of having the 3 by 3 convolutions rather than having 5 by 5 convolutions is big. So if you do a 5 by 5 convolutions, input number of channels is C, output number of channels is C. From the theory that we did, the number of parameters will be 25 C squared, and the floating point operations will be for each output size. That means output size will be C times HW. 25C operations will have to be there, then 25C squared HW. But if you have two 3 by 3 convolution layers, 3 by 3 convolutions, channel number C to C, C channels to C channels again. If you do that, then mm, mm, number of parameters will be reduced and the number of floating point operations will be reduced. That's a big advantage, as you can see. Okay. So also these two 3 by 3 convolutions have the same receptive field as a single 5 by 5 convolution. So therefore, the effect that you get is the same with less computation. So that's why people now use all 3 by 3 convolutions. And then you can see uh, after all max poolings are 2 by 2 strike 2, after pooling double the number of channels. And this is there. So you can see the size reduces, but the number of channels double, right? So these computational things I have written here. So you can see what the advantages are and disadvantages of this. Then after that, GoogleNet came. So GoogleNet, you can see it has a very strong stem. What that means is it quickly downsamples the image to reduce the computational load. So that's one thing. So the stem network for aggressive downsampling of the input. In AlexNet and VGG the early layers were very expensive. In the early layers, the sort of the feature map size or the structure size is large, the convolutions take too much computational power. That's the reason for this. And then they had the so-called inception module. There they had a combination of different types of convolutions, 1 by 1, 3 by 3, 5 by 5, and so on. This combination is called the inception network. So they thought it's good. Then they have finally so-called global average pooling. We will look at that briefly. So STEM network in GoogleNet is also analyzed here. If you like, you can go through it from the lecture that we did last time. I know that you can, if you want, you can look at it and analyze. So briefly about the inception module, you can see this is a local unit with the parallel branches. Local structure is repeated many times throughput, many times throughout the network. So use the one by one bottleneck. So when you use a one by one bottleneck to reduces the channel dimension before expensive convolution operations. This reason. So you can see it saves convolutions. But of course you have this one. Okay. Then the global average pooling is like this. No large fully connected layers are at the end. So you can see the fully connected layers had a lot of parameters in the AlexNet and even in the LeNet 5 that we looked at. But if you use so-called global average pooling, it collapses the spatial dimensions and one linear layer to produce a class force. Uh, because if you think about VGGNet and AlexNet, most parameters are in the final fully connected layers. This is why they do this. So what they do is they finally have they have a 1024 channels and 7 times 7 spatial extent. What they do is they remain those channels, but they average across the spatial dimension. This 7 by 7 array, they make it just one number by averaging. So you can see we call it 1 by 1. That's the global average pooling. It's a very important one. Mm. So they had this so-called auxiliary classifiers because by this time they did not know how to backpropagate through this network because so-called batch normalization had not been invented by that time. So therefore their gradients became zero, so they cannot backpropagate. So as a result, they had some auxiliary loss functions that after these stages they compute a loss and then so that the errors can backpropagate. This design is not required now. Okay, so we briefly talked about the ImageNet and ImageNet large-scale visual recognition challenge and how AlexNet won that challenge. We talked about it and it introduces max pooling, ReLU nonlinearity and large number of parameters. And VGGNet, all convolutions are 3 by 3 straight one paired one. All max poolings are 2 by 2 straight 2 after pooling double the number of channels. And GoogleNet, a STEM network, which quickly downsamples the image structure to make the number of computations quite less. An inception module, global average pooling, auxiliary classifiers, global average pooling reduces the number of parameters in the fully connected layers. Those are the contributions. Okay. Then after that, in 2016, a major contribution was made called residual networks. This is now there is an argument to understand this one. So I hope you can pay attention to that. Uh, so now by that time the batch normalization was there. I think batch normalization paper is a 2015 paper. So with batch normalization, deep models could be trained. So if we have time, we will look at batch normalization today. So AlexNet had 8 layers, VGG6 is 16 layers, VGG19 19 layers. Even more layers could be trained now with the batch normalization. But they realized that deep models are worse than the shallow models. So bigger is not better in contrast to previous experience. So initially they guessed deep models are overfitting since it's much bigger than the other models. Okay, now let's look at this graph. This is a test error, okay? Test error. That means in the totally unseen data, like we did today in the morning, in test error in the 10,000 test set images, as the iterations progress, 56 layer 1 is having more error than the 20 layer 1. Is the test error. Okay. Now, but if you think about the training error also, for that 50,000 training data, still the 56 layer 1 is making more mistakes. This cannot be true. When the number of layers increase, the network size is large, it should be able to at least memorize the training examples and make more low error. So they came up with a proof by construction. That proof by construction is this. Okay, in fact, the deep models seem to be underfitting since it's also performed worse than the shallow model on the training set. It is actually underfitting. 56 layer network has not been able to emulate the 20 layer network. So a deeper model can emulate a shallower model. Okay, copy the layers from the shallow model, and from the 20 layer model, we copy those 20 layers. And then we add identity layers. Layers that give you just one. Those layers we add. So if you do that, okay, 20 layers, those are the original layers, and then we add ones, layers that just produce ones, and it should give the same performance. But it has not happened, right? It has made the error worse. So thus deeper models should be at least as good as shallow models. So therefore they hypothesized this is an optimization problem. Deeper models are harder to optimize, and it is but in particular don't learn identity function to emulate shallow models. So they realized that these deeper models cannot learn the identity function. That means they cannot learn the mapping of one. Solution, change the network so learning identity functions with extra layers is easy. So they came up with a solution for that. What is the solution? This is the solution. So if you think about the plain block, X is there, input is there, convolution, ReLU, and convolution, and you get the output. So therefore, these convolution layers, they are saying that they cannot learn the identity function. That means here also just giving X, it's not possible. That's what they're saying. So what they did was they just connected X to the output. So what that means is if you just want this X as the output, you can just make them 0. So you can see what a clever idea, this so-called residual block. Kai Ming Hee is the author, as you know. So this is called the additive shortcut or the skip connection. It has to come after two con layers, X con, ReLU con, and then addition of this X and then ReLU. So also it makes the gradient flow much more efficient. So we will do a little bit of gradient descent today, backpropagation, then you'll understand that. If these set are set to 0, as I said, the whole block will compute the identity function. That's a ResNet. So what they did was a residual network is a stack of many residual blocks. Regular design like VGG, each residual block has 3 by 3 convolutions. Network is divided into stages. The first block of each stage halves the resolution, while stride 2 with stride 2 con and doubles the number of channels. And this thing was there in the VGG network also. So you can see input is there. So some aggressive downsampling is there with 7 by 7 convolutions and stride 2, I think. This is what I think what that means. Then pooling. So you can see the two con layers, and you can see the skip connection there. So this is the uh, stage 1. After the stage 2, you can see the number of channels 64 goes to 128, and the uh, size is halved. Size is halved due to the stride 2 convolution. This is the structure. And then finally, you have the pooling layer, fully connected 1000 and softmax. And this is the uh, average pooling part that we learn from GoogleNet. So you can see every year people are learning from the previous year and making progress. Okay. Use the same aggressive stem as the GoogleNet to downsample the input 4 times before applying the residual block. And like GoogleNet, no big fully connected layers, instead use global average pooling and single linear layer at the end. Okay, so ResNet had so many versions. So ResNet 18, so you can see ResNet 18 stem, 1 convolution layer, stage 1, 64 channels, 2 residual blocks, 4 convolutions, stage 2, number of channels is 128, 2 residual blocks, 4 convolutions. So you can see that there, stage 2, and stage 3, 256 not drawn here, stage 4, 512. It's drawn there. You can see that. That's the ResNet 18. Top 5 error in ImageNet. That means the correct class must be there within the top 5 classes predicted. 10.92. And when you had ResNet 34 layers, 8.58 was the error. So VGG, it had a large error with large number of giga floating point operations. These you can see extremely small compared to those. Yeah. Okay. So then residual networks had the so-called bottleneck block. So this is the regular residual block, and this is the bottleneck block. There you can see through 1 by 1 convolutions, 4 channels were reduced to C first. And then you run the 3 by 3 convolution. Then after that, with the 1 by 1 convolution, these C channels are expanded once again to 4 channels. So this has a computational saving. I have written that there. So you can understand that why that happens, because we have done the way to compute the number of floating point operations. So it is advantageous, slight advantages there. So, uh, I have done a small calculation here. If you like, you can go through that calculation. So, uh, yeah, I will not go through that. Yes. So for the residual network also, uh, here are the uh, G-flops and top 5 array and so on. So ResNet 18 and block type is basic. ResNet 34 is block type is basic. But after that, you can see they are using the bottleneck blocks. For ResNet 152 means 152 layers are there. So these are still very popular networks. Especially people use ResNet 50 a lot. Deeper ResNets 101 and 152 models are more accurate, but also more computationally heavy. Able to train very deep networks. Deeper networks do better than shallow networks as expected. So first place in Image and Large Scale Visual Recognition Challenge and COCO 2015 competitions, still widely used today. Okay, so then these are these ResNets, AlexNet 8 layers, VGNet 19 layers, ResNet 152 layers. Yeah. So then other design improvements were there. I will not talk about them too much, slight improvements. Uh, Bigger is not always better. I will briefly explain this diagram. For example, now this is the giga operations. This is the top one accuracy on the ImageNet. You can see if you take the early examples like AlexNet, giga operations was less, but the accuracy was 55% or something like that. If you take ResNet 101, okay, of course, some operations are there, but accuracy is very high. And then they had this inception networks. Those are ResNet 152 and so on. So they have high accuracy. So VGCs, you can see, they are very large and accuracies are less. So other ones are also there. So I have added some of them also, I think. Later in 2016, they had the combined model, so-called model ensembles. We will not study that. And then in 2017 came the so-called ResNext. ResNext. The thing about that is they use something called group convolutions. What that means is this. Now, if you take the so-called bottleneck residual block, you can see now every year they are improving. We said by this one by one convolution, the number of channels for C was reduced to C. So if you look at the LeNet 5, we had the number of channels 6, uh, 16 like that, right? We had them 16 or 10, I don't remember. Let me see. I have the code with me. I can, with the code, I can look at it. Uh, yeah, 6 and 16, right? 16, I think. 16 channels. So that you can reduce by one convolution to C. And then on that C number of channels, you run the convolution operation of 3 by 3. You can see when the number of channels is less, that means something like this now. So the input structure is, let's say, like maybe 64 channels, right? So if you want to run a 3 by 3 convolution on this, that convolution kernel's depth must be 64. So a lot of calculations will have to be done, right? As you can see. But if you reduce this depth of 64 by dividing that by 4 to 16 or something, not something, 16, you can see the size of the convolutional kernel. The 3 by 3 kernel has a depth, okay? That depth is reduced to 16. So this is the advantage of that. You can see that. So then once again, you expand it to 4 channels by another 1 by 1 convolution. So instead of that, in this one, they had G parallel pathways. So here is the input. What they did was uh, for C to C, they had a small c here. For C to C, they had a small c here. And this is the 3 by 3 convolution they carry out in with those small C channels. And this they raised back to 4 channels, 4C, and then concatenated over here. So you can see here, the concept of this small c is their contribution. So you can see that small c is 24, whereas big C is 64. So you can see the even bigger computational saving is there. That's one setting. And there are other settings. C is equal to 4. Yeah. So these are called group convolutions. Convolution with groups 1 is regular, and then convolution with group 2, which I have shown here. So you can see the input number of channels seen is there, and then this one happens with seen divided by 2. This one also happens with input seen divided by 2, and then you do the convolution, and then finally uh, you concatenate. So this is groups by 2. Then we have depth-wise convolution when the number of groups is equal to number of channels. So you can see that the depth of the convolution kernel is becomes 1 here because the depth-wise convolution. So this is very advantage. Uh, uh, they were they are used in very fast efficient networks. So if you're looking at REST next, you can see top one error is reduced in REST next. So then 2018, they came up with the squeeze and excitation network, also SCNets. This is also important because it has an important idea which is still used now. So that squeeze and excitation means you have C channels, height and width of the structure, we call it U, and then you sort of squeeze it to 1 by 1 times C, just a vector. And then you have so-called excitation multiplying by matrix W, by weights W, you still get a 1 by 1 by C. Then these are used to, now this is C number of channels. Now here this also has C number of channels. Each channel we multiply and weigh by each of these numbers. So this is a channel-wise weighing mechanism. So we can call it channel-wise attention also. Channels-wise attention. So now you know that in the new transformers that came in 2017 and adapted to vision in 2021, this kind of attention in a much more complicated spatial way is there. So this one is adaptively recalibrating channel-wise features responses by explicitly modeling the interdependencies between channels. So that interdependency is modeled by this weight matrix learnable. So those are again, this is the important contribution in the squeeze and excitation network. So then squeeze and excitation networks are there for ResNets. I will not discuss about that. Uh, it is okay. Uh, you can have a look at it. Then densely connected neural networks came in 2017 also. And then mobile nets, tiny networks for mobile devices, so embedded systems. So you can see in this one, depth-wise convolution is used. What that means is the number of groups is equal to the number of channels. We said that when the number of groups is equal to the number of channels, we call it depth-wise convolution, less computationally expensive. Yeah. Then there was another concept called neural architecture search. What that means is now we in the VGGNet we said 3 by 3 convolutions, this, that, and so on. So there, what they did was they had something called control network, and then they had child networks. So those child networks had some parameters, number of filters, the filter height, filter width, stride height, stride width, and so on. They had these numbers. Those numbers they learned. So once you learn those numbers, you have a network. You run that network and compute the accuracy. You feed that accuracy back again to the controller, and again change those parameters. So what we do manually by changing the kernel size, this, that, and so on, filter height, and so on, another neural network, this pink neural network that learns that. So this is called neural architecture search. So you can see that this one is extremely expensive. So this ran on 800 GPUs concurrently for 28 days. So you can see it has been extremely expensive, but it learned some architectures that are very useful, I think. But people don't use this neural architecture too much. Yeah. Okay, we'll summarize this one, what we learned. Early networks like AlexNet, Xyla, FergusNet, and VGG shows that bigger networks work better. GoogleNet, one of the first to focus on efficiency, aggressively downsample steps, and one by one bottleneck is there. Uh, Convolutions, global average pooling instead of fully connected layers. Global average pooling concept is very important. And then ResNet showed us how to train extremely deep networks limited only by GPU and memory and started to show diminishing returns when the networks got very bigger. After ResNet, efficient networks became central. How can we improve accuracy without increasing the complexity? So lots of tiny networks are at mobile devices, mobile net, shuffle net, and others. Neural architecture search promises automatic architecture design. So then I want to briefly talk about this efficient nets also. This is also a very important contribution. What they did was they had they studied uh, carefully how to balance the depth, width, and the resolution of the network. They had some parameterization for the depth, width, and the resolution, and so then they used neural architecture search to design a new baseline network and scale it up to obtain a family of models called efficient nets. So depth, scaling network depth is the most common way used in many convolutional nets. With scaling network width, number of channels is commonly used for small size models. Then resolution, with the high resolution input images, ConNets can potentially capture more fine patterns. So these were ideas that people had, but they did not know how to combine. So these people combined it. So you can see, so they have other networks also that you can see ResNet, ResNext 101 and so on, ResNet 50 and so on. So you can see with the same number of parameters, they were able to achieve extremely high accuracies with this. So still, if you want to use a good neural network, CNN for your work, you can use ResNet 50. Otherwise, you can pick one of those uh, efficient net B note, efficient net, and so on, efficient net B7, those ones that you can use. Then in 2022, they came up with another contribution called ConNext. It's a very recent paper. What they did was, I'll just tell you what they did. Maybe you will not understand fully what that means because we have not done the transformers yet. There was a transformer network called Swin Transformer. The Swin Transformer had some design choices. So transformers surpassed convolutional neural networks in 2021. Then they took those design methodologies in the Swin Transformer and then designed a convolutional neural network called ConNext that mimics the transformer's operation. So what they realized was, so this ConNext was also able to surpass the Swin Transformers one. So you can see the blue one is that. So Swin Transformers accuracy was this one. So they were able to bypass. So we can see uh, the design of the network architecture is very important in that case. So ConNext is also very important network. So if you ask what architecture to use, these instructions are from Professor Justin Johnson. And most of the slides are from him. Don't be a hero. For most problems, you should use off-the-shelf architecture. Don't try to design your own architecture. If you care about the accuracy, ResNet 50, ResNet 101, Efficient Nets B3 to B7, or ConNext are the excellent choices. Efficient Nets combine high accuracy with efficiency through compound scaling, and ConNext modernizes CNNs to rival transformers. So these are things that you can use. If you want lightweight networks, example mobile devices or your uh, small devices, you can consider mobile nets, shuffle nets, efficient nets, B0 to B2, etc. So this is the end of convolutional neural networks. But now we need to understand how we can train those convolutional neural networks. We will study that after the break. So we will meet at 12:05 or something. So it runs. So this was the problem. In the forward function, you have to return x. So it's running. So you can see the loss is reducing. Training loss must be reducing. Okay, right? I hope you are satisfied. Okay, so now we want to study backpropagation. We'll study it a little. Mm, We will not study the full backpropagation because it can take a long time, but we will study whatever we can. I hope everyone can hear me. So, as usual, if you have a question, please ask. Uh, all right. So these slides have been adapted from Professor Justin Johnson. Okay. So if you remember, about 2 weeks ago, we noticed that we need a score function and a loss function. In our code also, we had the score function and the loss function. So when you have a neural network, for example, input is 3072, that is like CFAR 1032 by 32 by 3 images, hidden layer of 100 nodes. This is a fully connected network. And output 10 nodes to represent the 10 classes. And based on the output, you can compute an error measure. So it computes a score, and then you can compute a loss based on that. Yes. So the score function will be from the number of data points, number of the dimension of the input image to the number of classes. So this can be, D can be 3072 and so on. And this can be 10. So each image is d-dimensional and I grow from 1 to n. So maybe if in the MNIST we had 50,000 images, right? And K can be 10 classes. So if we consider a fully connected network, nonlinearity is a max, W1x plus B1, and you have to apply the nonlinearity, multiply by W2, and you add B2 as a bias. And you know that when the nonlinearity is not there, it just is a linear network, so there is no much use of that. Okay. Then we looked at these loss functions, multi-class SVM loss. This is the score of the correct class. These are the scores except for the correct class. And then there's this margin of 1. Then you looked at the softmax loss. You e to the power the correct classes loss and all other losses. And this is like a probability, and you get negative log of that. That's a softmax loss. And then we realize that some regularization has to be added. Otherwise, the parameters can grow large, these W parameters. So usually if you take this network, it will be L, a function of W1, W2, B1 and B2, and which is the summation of all losses for each image, and then regularize W1 and regularize W2 parameters, quantities. So what we need to do gradient descent, that means move in the negative direction of the gradient uh, to obtain the better W1, W2, B1 and B2 parameters. I have made a mistake here. So you have to compute the partial derivative of the loss with respect to W1, partial derivative of the loss with respect to W2, and so on. Then we can use ADAM or the stochastic gradient descent. So for optimization, now if you have a closed form function, you can use quadrature programming in as done support vector machine or something. But in neural networks, you cannot do that. We will use stochastic gradient descent with many layers backpropagation to compute the gradient. So this gradient cannot be directly calculated. You have to do so-called backpropagation. We will understand what that means now. So in other words, the requirement is to find the parameters W1, W2 such that the loss cell gets minimized. We then use the optimization scheme based on the gradient descent. For this, we need the gradients um, of L with respect to W1, W2, B1, and B2. Mistake again. Then we can learn W1, W2, B1, and B2. However, L is a composite function of W1, W2, B1, and B2. Computing the gradient of L with respect to W on paper is very hard. This is a long network, a lot of parameters are there. Doing that on paper to compute the gradient is hard. For example, if you, instead of SVM loss that you had, if you change the loss to softmax, then you have to do the calculation again, write in the formulas again. So this is not possible. So therefore, what we do is build a computational graph using backpropagation and efficiently compute these gradients. So we will see how this is done. Now the chain rule. So this is a computational graph, as you can see. In this case, your Z is a function of f. Your x is a function of, the Z is a function of x. X is a function of t. And that function is f and g respectively. So you can see Z is Z is fx, x is gt. So then if you apply the chain rule, dz by dt, derivative of z with respect to t, is dz by dx by dt. So it looks like you can cancel these things out, right? So it is like that. It's not true, not so. No, this is the chain rule. So, for example, can you read this? So I hope you can understand that, right? This one, what you mean by this chain rule. Okay, but now it becomes slightly complicated if you have a computational graph like that. That means Z is a function of x and y, and Z is a function of t through this relationship. Then partial derivative of Z with respect to t is partial derivative of Z with respect to x times dx by dt, partial derivative of Z with respect to y times dy by dt. So I think these rules are, some of you may know these rules from high school. In this situation, it is convenient to call Z as the dependent variable and x and y the intermediate variables and t the independent variable. Okay. Now, if you have x and y as scalars, that one is easy. But if you have them like vectors, what is the situation? Now, you can see the situation here. There you can see y is a function of x through g, but x is a vector of m numbers. Y is a vector of n numbers. That means y is y1 to yn, x is x1 to xn. So from the previous one, you know that when something changes in x, something changes in z. When something changes in y, something changes in z. So that means in here also, whenever one of these variables change, they affect each one of them. So those are these quantities you can see, right? Partial derivative of y1 with respect to x1. How is y1 affected due to a small change in x1? Yeah. How does yi get affected due to a small change in xj? That is jij. So this is called Jacobian matrix. Jacobian matrix organizes all potential derivatives into an n by m matrix. It's easy to think when you think about Jacobian matrix, but practically we don't use Jacobian matrix to compute these gradients. Okay. So next, chain rule with vectors, Jacobian matrix. All right. Now you can see y is y1 to yn, x is x1 to xn. Then you have finally, finally z. Z is fy. So you can see you have to add over y's. Add over y's to find the partial derivative of z with respect to xi, right? You have to add over y's. So that we saw in this one also, because we have to add over these quantities, right? This layer, add over this layer. See, x1 and y, we have to add. So now you can see each one of these quantities, each one of them will have to be used when you want to compute one quantity, partially reset with respect to one of the x's. So there you can see, if you take all of the x's, grad x z, you can see you take the transpose of this matrix and multiply these numbers. I hope that is clear to you when you think about it a little. Thus, gradient of z with respect to x is a product of the Jacobian matrix and the gradient vector grad y z. This is a chain rule with vectors. So that's what you need to know. Okay, so we will do a little back propagation with scalars first. Okay, so this is the function that we want to use for back propagation. F x y z, x plus y times z. So first, let's take x plus y as q. So therefore, x y z is equal to q z. Very easy. Q itself is x plus y. So let's take these values -2, 5, and -4. Forward pass. X is -2, y is 5, z is -4. What is q? Q is this equation x plus y. Q is equal to 3. Now, how do you compute f? F is equal to q z. So -4 times -3 is -12. That's a forward pass. Now the backward pass. First of all, df by df. It's 1, right? df by df is 1, you know that. And then, what is df by dz? df by dz. For that, we have to look at this equation. df by dz is equal to q when you differentiate. So q is 3. So this 3 gets there. That's the derivative. So derivative of f with respect to the input variable is z. Okay. Next step. So what is df by dq? df by dq from this equation is z. So therefore we copy this value there. It's -4. Now we need to find it with respect to x and y. So df by dy, we know is df by dq by dy, right? That's the chain rule. df by dq is, we already know it's z. dq by dy is from this equation. dq by dy, it is actually 1. So you can see it's 1 by df by dq. So it is equal to z. So there you can see df by dq is, we have computed that as -4. Let me write that down. -4. So df by dy is minus 4. How about df by dx? Df by dq times dq by dx. dq by dx is 1. df by dq, we have already found. df by dq is minus 4. Therefore, this is also minus 4. So at once you see some pattern, right? Due to a plus sign, this gradient gets copied. Due to a multiplication sign, they sort of switch. 3 here, minus 4 there. So you can see that those patterns are there. This is the backpropagation with this very small graph with scalars. So now what is the general thing that happens? Now from the upstream, partial derivative of L with respect to Z is coming. Now we can compute the local gradient. That means the output of this node is Z. It has an input X, it has an input Y. So it has these two quantities we can compute partial derivative Z with respect to X and Z with respect to Y. So those we can compute because we know this function. We know what this F is. Then how do you find the downstream gradients? That means partial derivative of L with respect to X. That is partial derivative of Z with respect to X, partial derivative of L with respect to Z. So this is the chain rule, right? Because this chain rule. So it's very easy. So we call this the upstream gradient, we call this the local gradient, and we call this the downstream gradient. So to compute the local gradient, we multiply the upstream gradient with the local gradients. That's how you backpropagate the gradients. Backpropagate the gradients. So here is another example where we can do this. So in this example, you can see fxw is equal to 1 plus e to the power of minus w naught x naught, w1 x1, w2. So we have to multiply w naught x naught, this one. We have to multiply w1 x1, this one. And we need to add these two, this addition, this one. And to that we need to add w2, this one. Yeah. So here this quantity is now here, and you have to multiply that by minus 1, and you have to raise it to e to the power. This quantity is here. Yeah. Then you add 1 to that. This whole quantity, it will be bigger and bigger here. And you have to get 1 over that one, right? See, this is the final f, right? So I hope it is very clear what this is. And then we assume that we these numbers 0.2, 2, minus 1, minus 3, minus 2, and 3. We assume those. First of all, we have to multiply 2 and minus 1, so you get minus 2. Multiply minus 3 and minus 2, you get plus 6. You have to add those two. Minus 2 plus 6 is 4. And then you have minus 3 here. That also you have to add. You get 1 here. And 1 you have to negate. You have minus 1. E to the power of minus 1. This is what you're computing, right? E to the power of minus 1. And there you get 0.37, and add 1 to that, 1.37, and get 1 over of that. This is the final value due to this input. Now what we need to do is we need to backpropagate. So df by d partial derivative f with respect to itself is 1. Then okay, watch now. Then we need to compute the upstream gradient is known, it's 1. What is a local gradient? So this is like 1 over t, something like 1 over t, right? You know that 1 over t's derivative is minus 1 over t square. Do you remember? Do you remember in A levels you did d by dx? 1 over x. is equal to minus 1x squared, right? I hope you remember this from your A levels. So similar thing I have written. So what is the value of t? 1.37 is the value of t. Now I substitute it here. So 1 over minus 1 minus 1 over 1.37 squared. That number is there. So let me compute that. Do I have the calculators? I have the calculator, fortunately, this beautiful device. I'm happy that I have the calculator. Minus 1 over 1.37 squared. This turns out to be minus 0.53. That one, you multiply with the upstream gradient. Upstream gradient is 1. So this quantity, this is minus local gradient 0.53 multiplied by 1. That's how you get this downstream gradient as minus 0.53. Okay, that's clear. Then, what is the situation here? This is just x plus 1. If you differentiate, okay, this is t, let's put t there. If you differentiate that, you get 1, right? Derivative of t plus 1 is 1. So therefore, upstream gradient is minus 0.53, local gradient is 1, downstream gradient is the same thing. You just have to multiply upstream gradient by 1. Okay, that's okay. Now next one, this one. So derivative of e to the power t. We know that it is e to the power t itself, right? That's the property of e to the power of t. So we know that upstream gradient is minus 0.53. T is right now minus 1. So e to the power of minus 1 is, let me use my calculator to calculate that. E to the power of minus 1. That turns out to be 0.3678. 0.023678. So 9. And that one you have to multiply by minus 0.53. If you do that, you get 0.1, no, this one. This one. So you can clearly see that the downstream gradient is the local gradient, upstream gradient multiplied by the local gradient. So other ones I will not do. So the addition is there. You can watch at home how these things happen. Okay, maybe this one I will just do. So this is an addition node. Addition node. Upstream gradient is 0.20. And if you differentiate s plus t, let's call it, with respect to s, you get 1. If you differentiate it with respect to t, you get 1. Anyways, the derivative is 1. Local gradient is 1. So therefore, this 0.2 will be multiplied by 1 and put there. This 0.2 will be multiplied by 1 and put there. So you can say due to an addition node, you just get the upstream gradient repeated as a downstream gradient. So now here also you expect that to happen, right? This should go and copy here. This should go and copy there. See? But due to multiplication, what will happen? Let's check that. Due to multiplication, now it is like something like s times t. No? So partial derivative with respect to s is t, the other variable. Partial derivative with respect to t is s, the other variable. So therefore you can see the downstream gradient is, this is the upstream gradient, 0.2 has to be multiplied by this one to get this one, right? This 0.2 has to be multiplied with by this one to get this one, right? You have to multiply with the other one. So this, you can see, due to a multiply node, this is how the gradients backpropagate. So these patterns are there. So if you take PyTorch or TensorFlow, any other thing, these are autograd networks, autograd. They know how to compute the gradient automatically. How do they do that? They took each and every possible primitive node like that, multiply node, add node, uh, sigmoid node, these little functions, exp node, and so on. For those in C++, they implemented the local gradients. And then they build a computational graph and then they can backpropagate. This is what it is. They are autograd machines. Autograd machines. So now you know how they work. Perhaps some people will tell you, okay, these neural networks are there. They are black boxes. We do not understand how they work. I think we understand how they work. They are so complicated. That's why they are like magic. We understand how they work. Yeah, okay. So I think this is clear for you. But then now the thing is this now, this computation graph is not unique. For example, this whole thing, this whole thing, I can write this as sigmoid. This is a sigmoid function. So therefore, it's quite uh, possible to replace the whole thing with the sigmoid function. So therefore, that if your computational graph has the sigmoid node and your AutoGrad framework, PyTorch or whatever, has the local derivative of the sigmoid, then you can use that to do the backpropagation. So actually, for sigmoid, we know that the gradient, right? Sigmoid for sigma x, the gradient is 1 minus sigma x times sigma x. You can prove that. So you can use that to backpropagate. So I will not do that, but it is possible. Okay, so now you can see the pattern. If you take the add grade, this you have already seen, but I will draw your attention to that. 3 plus 4 is 7. That's fine. So this is the upstream gradient. Though it came from the upstream. We don't have to ask here how it came. Okay, it came from upstream. It's 2. Due to an addition gate, we know that it just repeats. Upstream gradient just repeats in the downstream paths. If you take the mul grade, you know that the upstream gradient 3 times 2 times 3 is 6. Upstream gradient gets multiplied by this 3 to get this 15. That's what we said. This is the mul gate. This is the copy gate. So if you have this input 7 and you repeat it in this branch and this branch, then your gradients 4 and 2 will be added. Yeah. Then you can have the max gate. So what about the max gate? Uh, think about this. So forward one, I can show you the maximum of 4 and 5. What is the maximum of 4 and 5? 5. We are asking like what is the maximum of 4 comma 5? Maximum of 4 comma 5 is 5. That's why you have 5 here. So how do you backpropagate the upstream gradient? So you can see mm, only this value now, the large value is affecting the output. So whatever this value, so long as it is lower than 0.5, does not matter. So therefore, there is no gradient here, 0. Not that no gradient, 0 gradient. This is this one. Just repeats. That's what happens due to max. For ReLU function, this is what is happening. Okay. So one thing is this. Now, if you know how to compute these gradients for all these nodes, local gradients, we know the forward path, we can implement the backward path. Okay. So let's see the network that we had. We have S node, W times X node. This is S node. And we have S1, W1 times X1, S1. And we have S2, this is S2. And we have S3, W plus 1, this is S3. So now they have written that as sigmoid function. This is L. So you can see this is how we can calculate the loss in this network, in this particular network. So I mean, loss can be should not be the sigma diode. You can have some subtract that with the ground truth or something and then square it or something. But right now it's okay. So then we need the quantities. Uh, this L is a function of S2, S3, right? So we need DL with respect to S3, right? That quantity we write as grad L. We only need to write, I'm sorry, we had only write it as grad S3 because it is always the gradient of L that we are computing with respect to S3. This is the DL with respect to DL. It's 1. Now for these, actually, we have to use the partial derivative notation. This is the partial derivative of L with respect to W3. Yeah. So therefore, W2. Therefore, only the with respect to variable you have to identify, and then it's well defined. So now we start with this and backpropagate. If you know that, we can write the partial derivative of L with respect to S3, that is grad L, the upstream gradient, times the local gradient. Local gradient means the sigmoid function's local gradient. And then for W2, grad W2, partial derivative of L with respect to W2, grad S3. What's the reason for that? What's the reason for that? Because it's an addition node. Grad S2, it's an addition node, grad S3. Grad S node, grad S2, because it's also an addition node, and so on. So I will animate this through properly. Okay, forward pass, backward pass. So and that is this one. So the concerning these two, we have it. Concerning this, we have this back propagation. Concerning these two, we have this. Concerning these two, we have this. Concerning these two, we have this. Okay, so now what you saw is if you know the forward path, you can compute the backward path and compute the gradients with respect to all the variables W0, W1, and W2. If you know the gradients, you can use gradient descent with a learning rate. I hope that these ideas are now clear how a neural network is optimized. Any questions? Okay. So I have a pseudocode here, but I will not go through the pseudocode. Um, I got ChatGPT to write it for me. But I will maybe hint at one thing. For example, if you take the add node, so you have the value of that add node. And how do you do the gradient computation? You have the inputs. You have the gradients. You have the value. Because it is add. For all the inputs, you add the upstream gradient. For all the inputs, you add the upstream gradient. Upstream gradient gets repeated. For multiplying, the value is actually uh, input 0, input 1, you multiply. That's the multiplication. But what is the downstream gradient? So input 0, the gradient is self.grad, that's the upstream gradient. Self.input C1, the other one, is value. For this one, you get the local gradient. The local gradient becomes this other variable. Yeah, that's what happens with the multiply node. So you can see if you implement these little local gradient computation nodes, then it is possible for you to backpropagate. I will not go through those further. So that computational graph I implemented through PyTorch. So I defined x0 and x1 as required gradient folds. And W0, W1 and W2 I implemented as required gradient through. And then I initialize them with those values that we used in the computation. And then in the forward pass I wrote is it is this sigmoid function. And the loss source I wrote a loss MSE loss. In the previous example, we did not have a loss, we just had the sigmoid output as a loss. Then all you need to do is you don't have to do manual calculation, you just have to say loss dot backward. Loss dot backward, that's all. Then you can do a gradient descent with the learning rate. So I hope that is clear for you. So then without the AutoGrad also I have implemented uh, what I wrote in the slide. I have implemented that. So you can see x naught, x1, y true, w naught, w1, w2, and then z this one, math e to the power the sigmoid function and the loss. Then all other uh, backward pass derivatives I have written here. And then the gradient descent part also. So you can see these are very easy things, not hard, but they become a little bit complicated when you have vectors and matrices. I will only show you this, but I will not go further. You can read the slides if you wish. So if you have x and y as scalars, x is a scalar, y is a scalar, then partial derivative of y with respect to a is a scalar. If x changes by a small amount, how much will y change? The derivative is a scalar. That's, I think, clear. But if you take x to be a vector and y to be a scalar, derivative is a gradient. That means for with respect to each component of x, each n component of x, you have to compute the y's derivative, partial derivative with respect to each n. So for each element of x, if it changes by a small amount, how much will y change? That's the question we ask. The gradient is of the same shape as the input x. This is what we need to remember. The gradient is always the same shape as the input variable. Okay. Then we have the vector. Then we know that we have the Jacobian. We did that at the very beginning. Jacobian is of the size n by m, but the derivative is of the size of x. Okay, so let's see with backpropagation with vectors. So z is the output vector. Its size is dz. X is an input vector. Size is dx. Y is an input vector. Size is dy. The loss is a scalar. So partial derivative L with respect to x is always has the same shape as x, that we have to remember. So upstream gradient will have the shape z, and these are the local gradients of the Jacobians. Z with respect to x, dx by dz shape. Z with respect to y, dy by dz size. What will be the downstream gradient? So this dx by dx, this one will be multiplied by this one. So you can see the sizes, they match and you get this size. This correct, right? Sizes match. And of course, the derivative must be of the size of the input variable. So that means x's size of x. You can notice that it is correct. Similarly here, so dx by dz is the size of this because it's Jacobi. And when you multiply by the size dz, you get size dx. Matrix vector multiplication is what is happening here. So Jacobian matrices, there are two Jacobian matrices. I hope that is clear. Okay. So now one more example, we'll take backpropagation with the vectors element-wise ReLU. Now think about this. Now ReLU function. ReLU function means you just guess the maximum with 0. So when the input is 1, Max, what do you have? Max 0 and 1. What is max 0 and 1? 1. When the input is -2, what is max -2 and 0? 0. When the input is 3, what is max 0 and 3? 3. When the input is -1, what is max 0 and -1? 0. So you can see the output is correct. Now, how do you backpropagate? So think that this is the upstream gradient. Don't ask how this was on. We write it. This is the upstream gradient. We take it like for the example. Partial derivative L with respect to y. Of course, it must be of the same size as y. Then Jacobian is this. That means when this is 1, it affected that, right? So that's 1. When it is negative, it does not affect that, it's 0. It does not affect any other element because this is element-wise max ReLU. Because it is element-wise ReLU, element at location 1, that is this one, affects only the element at location 1 there. It does not affect the others. So therefore, all these elements are 0. If you take the second element, it does not affect any one of those because it's a negative element. So they all these are 0. Third element is a positive element, 1. Last element is a negative element, nothing. So now you can see Jacobian. This Jacobian is sparse. Sparse. That means almost all the values are 0, only a couple of values are 1s. So therefore, doing this Jacobian vector multiplication is a stupid thing to do. You don't have to do that many multiplications. If you multiply, you can get it. But if you multiply, you can get it. But it's 4 and 5. That's a gradient, but the matrix multiplication. But it's not required because you can write a rule like that, right? If the input xi is greater than 0, that means if one of these values is 0, copy the upstream gradient. Copy the upstream gradient. If the input value is negative, put 0. If the input value is 3 positive, copy the upstream gradient. If the input value is negative, put 0. So isn't that rule much more easier than the regular vector Jacobian multiplication? So from this example, what you notice is in frameworks like PyTorch and so on, you don't compute Jacobians and implement backpropagation. You have for each of these little nodes like max pool, this, that, and so on, they have rules like this. Much more simpler rules, computationally less expensive rules like that. Then you can do these things. So we should not implement them using as a Jacobian. Jacobian should not be computed in other words. So never explicitly from Jacobian. Instead, use the matrix multiplication. So actually, I have done this computation using things, a torch, and I rewrote this one, and then I get the grad by also upstream gradient. Then I did loss. Uh, Whatever. I have shown the Jacobian also. I cannot understand some of these things now. Uh, the Jacobian also I wrote, but it's not useful. So this is you should not never compute. But I just compared Jacobian to show you that what we wrote there is correct. Okay. So matrices one I will not cover, but you can watch that if you like. I have some examples also. These are from Justin Johnson. You can see. With them and see. Yeah. Okay. Any questions about backpropagation? So backpropagation, we need the chain rule. Autograd is implemented in these ones. So the thing is downstream gradient is equal to the local gradient times upstream gradient, which you have seen here. Backpropagation with vectors, we need the Jacobian matrix, but we never compute the Jacobian explicitly. We come up with some rules. Jacobian with backpropagation with matrix multiplication is also possible and is very important uh, 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 neural networks because these out structures, input structures, and output structures are matrices. They are high dimensional matrices. They are tensors. Okay. Any questions? I hope things are okay. Okay, so I will give you some ideas about training. Not to some tools that are required for this, and activation functions, weight initialization, and so on. Yeah. Training CNNs. Batch normalization. So thing about batch normalization is this: when you get images, those images can have many numbers. Therefore, they are not sort of centered around number zero, because these numbers are from 0 to 55, like so many numbers. So to make the computations better, and to make the computation as much more suitable to the activation function, we actually subtract the mean and divide by the variance, as you see here. Subtract the mean and divide by the variance, like z-score calculation. So they say it reduces the so-called internal covariate shift. That means when the data changes from batch to batch, it reduces the shift that happens. But this is not a very profound explanation. Okay. So how batch normalization happens is this. So this is, think about this as uh, the number of images in batch size, and each image is d-dimensional. Think about that like that. So what they do is they compute a mean mm, in this direction, mean in this direction. So per channel mean shape will be D. And the standard deviation, also per channel standard deviation shape will be D. So normalization happens, and this shape will be N times D. So this is, you can see the mean, they have subtracted the mean and divided by standard deviation. But they have added some small number to prevent the divided by zero error. So one thing is, sometimes this is very hard to enforce this constraint, zero mean and unit variance. So therefore, they usually have some learnable variables, gamma j and beta j. Output shape is n times d, yij is n times d. So they learn gamma and beta, but if gamma is sigma and beta is mu, this sigma and this mu, so you can see this acting like an identity function transformation, the combination of these two. But the problem is mu and sigma estimates depend on the mini batch. So we can do it only for a batch. But this mini batch thing is not there in testing time. So in the LeNet also, we took 64 images at a time, as you remember, right? But in testing time, do you have those 64 images? We don't have them. So as a result, we cannot do this calculation at the test time. So only way is to compute this mu and sigma during training time and keep those values. So during testing, batch normalization becomes a linear operator. Okay. So you can see in the testing time, what we do is we use this training time mu as a value of running average, and sigma squared as running average. So per channel mean shape is D, per channel standard deviation shape is G, and then we normalize using those numbers. And of course, we have this gamma and beta thing also. During testing, batch normalization becomes a linear operator. So you can see these are linear operators. Uh, can be fused with the previous fully convolutional conveyor. So therefore, no overhead during the testing time. So batch normalization is very, very useful, extremely important. I will not talk about how batch normalization can be done for convolutional networks, but these batch normalization layers are inserted after FC layers in fully connected networks. This FC, this batch normalization. So that when it feeds to nonlinearity, for example, let's take some nonlinearity. Let's take the stupid sigmoid nonlinearity or something like that. There you can see that after that batch normalization, sort of the data will be in this region, right? They are normalized. So that means they will not go into this region and that region of the sigmoid function where the gradient are zero. Gradients are zero. Here the grad is zero because function is horizontal. Here also the grad is zero. So you can see because of the batch normalization, the input activations do not move into the gradient zero regions of the activation function. That is why it is very important to do batch normalization. So you can see when you do the batch normalization, the accuracy has improved. Uh, improved here. But if you do, then you can increase the learning rate also. So the accuracy can further improve. But this is not theoretical well understood before it behaves differently during training and testing time. Then there are other things called layer normalization, instant normalization, and group normalization. You can study about them if you like. I will not talk about them because it's too much material. Of course, if anyone wants, I'll be more than happy to explain. Okay, let's briefly look at the activation functions. Okay, so we know that when you have a perceptron, like a neural network, perceptron, so we have the input x1 to xd and the weights w1 to wd. We multiply x and w and we conform wx and we have a bias also. And then we apply nonlinearity. This is what we call it as the activation function. So perceptron is linear classifier. Activation when you apply Wx plus b, activation is Wx plus b, and we apply an activation function on top of that. Nonlinear activation function is extremely critical. As you know, without that, you cannot have nonlinear classification boundaries. Activation must be close to zero and mix of positive and negative numbers, this activation. So you can see the value of batch normalization there. So activation functions, we have already looked at them. The very first one that people used is, I think, the sigmoid function. Now, sigmoid function, you can see starts from 0 and goes to 1. And in this region, it has non-saturated value. This is saturated, this is saturated. Gradients are 0 in these regions. Gradient is 0. Gradient is 0. Here, the gradient is positive. But you can see it is not zero-centered. But hyperbolic tangent, if you take, it's zero-centered. See, zero-centered, but again, it has this problem of a saturation effect. But if you take the famous ReLU function introduced in AlexNet, it has a nonlinearity. It has a non-differentiable point here, but it does not have this problem of saturation here. But the gradients are 0 in this region. But if you take the leaky ReLU, gradients are not 0 in this region also, but not used too much. ELU, that's a version where the non-differentiability is also gone at the cost of having an e to the power. But usually this computing, this e to the power thing is not so complicated in a GPU. So therefore it does not matter too much. Okay. So one thing is this, saturation kills the gradients. So we looked at backpropagation. So now you know that in the backpropagation, the upstream gradient is multiplied by the local gradient to compute the downstream gradient. This is what we saw. But for this sigmoid function, you know that the gradient is 0 here, right? Here is 0. Here gradient is positive in this region, sort of from here to there. So you can see the upstream gradients are just killed if your activation falls into these regions. That's the danger of this function. There are other problems also. I will not explain those other problems too much. But this is the greatest problem of the sigmoid. So sigmoid function should not be used as an activation function. Similarly, problem is there in the hyperbolic tangent function. Saturation kills the gradients, but it is zero-centered. And then ReLU function is very nice. Uh, it's of course, non-zero centered output. That's okay. Once values are 0, gradients are 0. That problem is there. So that means here, uh, mm, uh, if it runs into that, we will see another diagram for this. Does not saturate in the positive region, computation efficient, converges much faster than the sigmoid and hyperbolic tangent, 6 times faster. Only the sign bit is needed to backpropagate because um, uh, when the activation value is positive, it's in this region, negative in that region. So in this region, gradient is 1. Very easy. Only the sign is required. So long as the inputs are positive, fine. So, but there is a thing called dead ReLU problem thing is there. Occurs when ReLU is outside the data cloud. So think that this is the space of the weights, and activations happen in this region, and the ReLU function is outside that. Then you will always get 0, and then gradients will never backpropagate. This is called dead ReLU problem, but this is only for one example. But when you have large number of images, this does not usually happen. But we want the ReLU to stay intersecting with the same parts of the data cloud. So sometimes initializes layers with ReLU with slightly positive biases. So leaky ReLU, it prevents the problem of dead ReLU problem because it has a gradient in this region also, leaky ReLU. Sometimes the people have the parametrically rectified ReLU also, where they have some alpha parameter that learns this quantity, a learnable parameter there. So because this is otherwise becomes a hyperparameter, this 0.01. So nonlinear itself is learnable in the ReLU. So then, of course, ELU that uh, has the reduces the problem of non-differentiability, avoids a non-differentiability at 0. But its computation is slightly expensive. Does not matter too much. But the thing is, by changing the activation function from ReLU to leaky ReLU to preLU to whatever, you don't gain much. You see, sort of like almost the same, right? These are almost in the 90s. So therefore, don't worry about this too much. Only thing is, don't use sigma or hyperbolic tangent. If you don't use sigma or hyperbolic, sigmoid or hyperbolic tangent, you are fine. Don't think too hard, just use ReLU. Try out leaky ReLU, ELU, CELU, GELU, anything do if you need to squeeze the final 0.1% improvement. That's about the activation functions. Data pre-processing is there. So data pre-processing thing is this: when you get images, assume that these are two-dimensional images, maybe the mean is somewhere here. When you add them and get the mean, divide by the number of images, the mean is there. That's bad. You can see for activations, this may affect. So we can do mean centering the data. Mean centering the data can be done. So data comes here, and you can divide by the standard deviation also. So these kind of things are very important. Usually you do this pre-processing, and then there's a thing called whitening also. These things you can do. Before, for example, before normalization, maybe your one data set is here, the other class is there, and this line is separating line defined by the W, right? If W slightly changes, you know that this line will move like that. So this is bad. It can change the classification. But if your data is centered, the slight change in W does not affect that, right? Slight change in W, that means when this line slightly rotates, does not affect that. So that is the value of this normalization. So other people have also used data preprocessing for CIFAR 10, for example. They have used, they have taken these 3 by 32 by 32 by 3 color images in CIFAR 10. So in the AlexNet, they subtract the mean image. Consider the mean image and subtract that away. So in VGNet, subtract per channel mean, and divide by the per channel standard deviation in the ResNet. So these things people have done to pre-process data. Okay. Then let's talk about the weight initialization. Now, so in the convolution neural network, we have the weights. That means weights of the convolution parameters. So the weights in the fully connected layers. How do you initialize them? So initialize the weights W and B with 0 is inappropriate, because if all W's are 0, all B's are 0, gradient is 0. So nothing will happen. So you have to initialize. So you can initialize. One option is to initialize W with normally distributed random numbers. then you can an activation like hyperbolic tangent uh, is fine. So, but what happens is what they have noticed is when this goes from layer 1 to 2 to 3 and so on, they become very close to 0. That is bad. So, so therefore, all activations tend to 0 for deeper network layers. So what do the gradients dl by dw look like? They all will become 0, all 0, and then there will be no learning. So this is a problem. So then what they discovered was mm, you can increase it. If you increase it, what will happen is it will become -1 and 1 always. -1 and 1. So the local gradients are all 0, no learning. I'm not too sure whether I make a mistake here, but that is okay. Please ignore that. I don't know what actually happens to gradients here. Then there is this initialization called Xavier initialization. It is just right activations are nice scale for all layers. So there you can see you get the random numbers and you divide by square root of the input dimension, square root of the input dimension. So then you can see the weights are nicely distributed. So learning well happens. So we can just prove why that is correct. So what we want to do is the out variance of the output variable should be the variance of the input variable. So therefore, data is nicely distributed around 0. So you can, if you consider y is equal to wx, you can see y is equal to j goes from 1 to d in xj, yj, wj. Now let's see this. Variance of yi is equal to d in times variance of xi, wi. So if you compute the variance of that, you will get mean of xi squared times mean of wi squared, mean of xi squared, means of wi squared. Assume x and w are independent. So therefore, this we can, if we assume that x and w have 0 mean, then this is the variance of xi, variance of wi. The two means are 0. Then you can see to retain the output variance as that of the input variance, what you need to do is variance of wi must be 1 OD. Then you can see the variance of the input output. This is yi. Sorry, this is variance of yi is the variance of xi. So the variance continues to be the same as you go through the layers. That's why you have to initialize the weights dividing by the square root of the number of square root of d in input size. So, but this fails when you have residual connection, ResNet. Oh, I'm sorry. This fails when you have the uh, ReLU activation. ReLU activation. So for ReLU activation, it has been proven that you have to it has been shown that you have to divide the multiply by square root of 2 divided by d in. When you do that, the problem is solved. So this one is called Kaiming initialization after Kaiming he who wrote the ResNet paper, and it's called MSR initialization also. Why? Because he was working at Microsoft Research at that time. So, and then for weight initialization for uh, residual networks with ReLU. So there is a problem here for residual networks. You know that output is fx plus x because we have it like that, the skip connection. And so variance will always be greater output variance. So there the solution is initialize the first column layer with MSRA, then initialize the second column with 0. So these weights you initialize with MSRA, okay, I mean, these you initialize with 0. Then this will remain. So you can see there are different ways of initializing. Weight initialization summary. Weight should be small but not too small to facilitate backpropagation through the activation functions. Weight must be 0, output 0, gradient 0. They must not be the same. All neurons produce the same output. Okay, now that's a mistake I made here. They must not be the same, then all neurons will produce the same output. Yes. Weight should have a good variance. If the zero-centered activation function is used, use Xavier initialization. If ReLU activation is used, use timing initialization. If ResNets are used with ReLU activation, first convolution layer timing initialization, second convolution layer zero initialization. And those are the rules for await initialization. Okay, without hmm, going for the regularization, because there's a little bit of things, we will stop here for now. If you have any questions, you can ask. Otherwise, we are done for today. I have uploaded some one tutorial, please do that tutorial. And if you need any help with that, maybe I can have extra session or record the answers and upload. If you request, you can request over WhatsApp if you need those. I will try to make some more tutorials and upload so that you can prepare for the exam. Because you saw I did not teach for the exam. I taught you to enable you to do something, but exam preparation is also required, right? For that. Yes. If you have questions, we can discuss. Otherwise, you can log off. Thank you. Thank you, everyone.